Hopefully everybody knows me.
Just keep it.
Okay, I should stay like this, yeah?
No, it's at the front.
So can everybody hear me? Great. Now I feel like a rock star with the real This is called, of course, the degree block formalism, because the way you divide the classes is you divide them by degree. Right? So you say nodes of degree 1 are all the same, nodes of degree 2 are all the same, nodes of degree 3 are all the same, but the way each degree behaves can be a little bit different. So if you think in terms of a random walk, how does it work? So it's the classical idea of you get drunk and you try to go back home, so you walk around back and forth. But now you have a bunch of people, a bunch of these little pills going back and forth. You can of course diffuse with some diffuse rate that goes as 1 over k. And what this means is basically whenever you're in a node and you need to choose where to go, so like when you're in an intersection, you need to choose where to go, and you just randomly go to one of the roads at random, right? So if you have 1,000 walkers, they get divided over the possibilities. So the probability that each node, that each walker follows each edge is just 1 over, or rather the number of walkers divided by the degree. So that's why you get that diffusion right over there. And then you define basically what these are called the block variables, right? So these are the variables, so like they're macroscopic quantities, like we defined before, but now they're indexed by the type of node that you're considering. So here WK is the number of walkers in nodes of degree k. And of course, the way you do this is very simple. You just sum over all the nodes. Over all the nodes I. Over all the nodes that have degree k. And so you go all of them. You keep only the ones that have degree k. And then you count and you just sum how many walkers there are in that node. Yeah, that should be ki equals k. That's what I was confused. Not 1. And then of course you divide by how many nodes you have of that degree. And that's how you calculate the total number of walkers in nodes of degree k. Right? And so this is called not the homogeneous mean field approximation, this is the heterogeneous mean field approximation, right? Because you're introducing heterogeneity in the system. Not everybody is exactly the same as everybody else. Some are more equal than others, if you want. And you should be able to read that over there, but you can. And what it says there is simply that, for some reason that font became very small, is you just treat all nodes of degree k the same, right? Is what I already said. So now you can define, of course, the degree block master equation. Again, it's always the same game. You have some configuration sigma. You count how many things get into sigma, how many things get out of sigma. So the variation on the number of walkers in nodes of degree k times t. And R is, of course, just the diffusion rate. K is the degree of that node. And you're summing over all the nodes k prime, so over all the degrees k prime. And the probability that the node of degree k prime is connected to node of degree k times the number of walkers in the nodes of degree k prime divided by k prime, right? So if you think about it is, I'm a node of degree k. What is the probability that I'm connected to a node of degree k prime? And then how many walkers are there? And what's the probability that I get them? Right? So this is what this is. Probability of being connected to a node of degree k prime. So this is probability of k prime given k. The number of walkers in nodes of degree k prime on average, divided by k prime, because each walker will choose at random where to go. If that node has a degree k prime, then I only get wk prime over k prime. And this is how I get walkers into this class, into a node of degree k, and this is how I lose walkers of degree k. So all the walkers that I have go away somewhere else. Because at each time step I assume that all the walkers move. So this is, like I said, the change of number of walkers of the degree k. The conditional probability that an edge connects a node of degree k to a node of degree k prime. So this is the conditional probability, p of k prime given k. So if this is an edge and it's connected to a node of degree k, what is the probability that the other side is connected to a node of degree k prime? And this is just the diffusion along the edge. And of course, you get the 1 over minus k, or 1 over k for that reason. So for uncorrelated networks, now what this means is that there are no explicit degree correlations. So the probability that the node of degree k is connected to a node of degree k prime is the same regardless of what k prime is. Right? So p of k prime given k is given just by the degree of k prime and the number and probability that the node is k prime, and because that basically tells you how many possible edges of that degree class can connect to me, but it doesn't depend explicitly on what my degree is. It only depends explicitly on the k prime and the average k. So when using this approximation, our master equation now becomes something like this, so it simplifies a lot. So of course, as we saw before, the equilibrium distribution, one way of obtaining it, and this leads us to the detailed balance condition, is just setting this differential equation to 0. And when you do that and you solve, you get something like this. So omega, the number of walkers in node of degree k times t, just k over h k, the sum over all degree classes k prime, p of k prime. So how many, you can think of it, of how many nodes of degree k prime there are, times the number of walkers in each node of degree k prime, and that's how many walkers you get there. And what this means is basically what each degree class basically gets an average number based on its own degree and how many total walkers there are in the system. Because from normalization, you know that if you sum over all the walkers in a class of degree k, you multiply the number of nodes in degree k, you just get the average number of walkers. And so what you get is something exactly like this, which is very, very simple. And what this is telling me is something very interesting. Right? Even after all of these things, and all of these crazy calculations, you end up with something very simple, and you say that the number of walkers in a node of degree k just goes as k. Right? It's proportional to k. So the more edges I have, the easier it is for walkers to reach me, so the more walkers I'm going to end up having on average. With, of course, fluctuations and all those things, which is what it says here. Yes. Higher degree nodes have more walkers, and you can think of this as basically meaning that nodes with higher degree somehow are more important for this process, right? Yes. So they're more important, and so it gives you a very empirical and very simple definition of centrality on the network. Right? So the simplest centrality is degree centrality. You're more important if you have more, if you have a higher degree. Now, some crazy people, many years ago, almost 30 years ago, decided, okay, but if we have a simple way to measure how important a node is, and we have a network that represents how web pages are connected to each other, we have a way of finding which pages are important, right? And now we have Google, which is basically based exactly on this idea, which is very simple. Is you basically simulate somehow a random walk in the system. You watch and you see where the walkers end up, and then you rank the pages based on the number of walkers that ended up there. Right? So if yesterday evening, if you Googled ProfLab, you would end up with something like this, and you would rank things, and you could see that the results are pretty reasonable. So how does PageRank actually work? So PageRank is very simple, and it's defining, and so it's taking the idea of random walker one step further. And basically what it's saying is the importance of a page is the average of the importance of all the pages that connect to it. Right? This is what this is saying. So pi of I, so pi here represents page rank. So the page rank of page I is basically the sum over all the page ranks of all the pages connected to I, divided by the degree of those pages. Right? So you can think of this basically as being a random walk, where you're basically counting how many walkers end up in my page, and that's just the average of all the walkers around you. So it's a very simple walk. And you can represent this basically as being the stationary state. So this is what corresponds basically to when we made time go to infinity before. So the page rank times t plus 1 is equal to some matrix and times the page rank vector times t. And this matrix is basically the adjacency, the transpose of the adjacency matrix multiplied by the inverse of the diagonal matrix, where each element in the diagonal is the degree of the node. Right? So it's basically the adjacency matrix divided by ki. Now there's a few problems with this. First, you have dangling nodes, right? Because now the network is directed, so you can have problems. You can have cases where walkers can reach a node very easily, but then can't leave the node, right? Because there's no out degree. So out degree is 0. So and what this means is that this becomes a trap for nodes. And the way you solve this is you connect all dangling nodes. Right? So in a very simple way, you cheat and you say, actually, if your out degree is 0, actually I'm going to replace your out degree of 0 by n. So I'm going to connect you to everyone. If you're not connected to anyone, I connect you to everyone. Right? Which if you think about it, it's kind of weird. They say, okay, why not? And empirically, if you think about it a little bit, because of the way the random walk is defined, you're saying, okay, I arrive in a node, I don't know where to go, I have nowhere to go, so I'm basically jumping at random somewhere else in the network. I'm just saying, okay, I'm on the dead end, I'm going to jump there and start there and try looking for something else over there. And empirically, that's what this connect to everyone represents. Because then, if I connect it to everyone, and I'm choosing one of the connections at random, I'm basically jumping randomly to somewhere else in the network. Another problem is slow convergence, right? I mean, you can have problems where this doesn't converge very, very quickly, and the way you fix that is you add the damping factor, right? And the slow convergence can come, for instance, if you have like a long strand of nodes connected to other nodes like this, then the walker will kind of fall down this hole, and then you take a long time to come back out again. Right? And the damping factor, it basically says that at each time step with some fixed probability, you can jump at random somewhere else. So it's exactly the same thing as you do here. Right? Here you jump somewhere else, basically by connecting these nodes with everybody else. Here you just randomly jump somewhere else. And the way you do that is you modify the matrix a little bit. So now the transition matrix, which originally was just a very small modification of the adjacency matrix, is now something a little bit more complex, right? Because now we have this alpha, and this is what that damping factor was. So this is the probability that you just jump at random somewhere else. For magical reasons that were never really explained in the original paper, this was set to 0.15, and now everybody uses it as 0.15. So it became written in stone. And so you can write this as basically C being the stationary state of this type of process here, where this G is this, what people call the Google matrix. Now, this is a Markov chain that has very interesting properties, right? It's memoryless. It's Markov, so memoryless. So you don't remember how you ended up in the node that you are. After all, you're drunk, you're just walking around randomly. And you just know how you can go somewhere else. It has a stationary state. For a Markov chain, a Markov process of this type, to have a stationary state, for you to be able to say, let t go to infinity and see what happens, you need to have three conditions. The matrix has to be stochastic. And what this means is that if you sum over all the columns, you need to get 1. And that basically means, which you kind of get by construction, because you're saying at each node, you're choosing where to go completely at random as 1 over the number of degrees. So if you just sum over all the weights for each edge, you get 1 by construction. It has to be irreducible. Right? And what this means in practical terms is the graph has to be connected. So, and you basically fix this by connecting the dangling nodes to everybody else. You by automatically made it all connected. And it has to be aperiodic. Right? So it can't be like kind of a circle where you just go around in circles like that. And you get basically these three conditions more or less for free, with these little modifications that you add to make the process work. And based on this, you can build a multi-billion-dollar company, which is kind of cool. But then you still have this problem, right? You still have to solve this. You have this gigantic matrix, which in the case of actual Google can be like 1 trillion nodes, order 1 trillion nodes. And you have this vector, and you have to basically find this, and this corresponds basically to the eigenvector corresponding to eigenvalue 1. Because you can kind of see that it's like if you had a lambda there, and lambda is equal to 1. And the way you do this is you iterate, right? So you guess what the values of that vector are. So you guess a value for this vector over here. You multiply by this matrix, you get another vector, and you repeat forever. Right? So what this means is that you get at each iteration, you get another approximation on the thing, and eventually this should converge, right? So empirically, you can think of this as being you basically simulating the system, right? You put walkers somewhere on the network, and that's your initial guess for this vector. You run one-time step, so you follow the connection to the network. You see where your walkers end up, and then you keep redoing it until it converges. Right? Now here convergence is represented basically by saying that the vector you put in is equal to the vector you get out. Right? Nothing changes. And that means that you get to the state where there is no variation in that sigma, so the number of things going into the sigma, the number of things going out of the sigma, so you're in the stationary state. So you stop basically when these two things are the same. And here is a little simple example, right? If you have a matrix like this, you have this problem, you have a dangling node over there, so you need to connect it to everybody else to fix the problem. And now you get another demo, which is cool. Yes, and please don't be shy about interrupting me and insulting me and all those things. Go for it. Also, rotten fruit is also good. No. So somewhere over here. So this is basically just a simple representation of that network I just showed you before, so it's a very simple thing. And what this program is doing is basically reading this thing, looking at the network, fixing those problems I mentioned, so you have the dangling node, so it's connecting to everyone, and then just doing all the thing, and then it's running this power method thing. So let's see. Poof. So that can actually see something. So here you have the original network, so which corresponds basically to the little drawing I just showed you. This is a Google matrix, so this is how you fix it. So you will notice that, for instance, here you have this line, which is all zeros, basically corresponds to that node in the center that's not connected to anyone. The Google matrix, since it's the transpose of this, that corresponds to this column, and you'll see that it has basically connected to, now it became connected to everyone with weight 0.2, which is just 1 over the number of nodes. And there's a couple, and basically everything else remains more or less the same, just normalized differently. So if you sum over all these columns, you get 1. And this is basically the iteration of the power method running on this thing. Right? So I start with this initial guess. So I say 20% of my walkers are in each node. I can start with whatever guess I want. It doesn't have to be this, it can be whatever you want. You can even start with all the walkers in one specific node and then let it run. Of course, that will let it take more time to converge, because then you have to wait for all the walkers to spread a little bit, but it will end up there. And here what you have is basically all the iterations. right? So I'm showing you the vector of my vector of page ranks. This one that you see here at the end is basically the sum over all this, just to show that this remains normalized. And you can see that it converges relatively quickly. Right? So here you get, in 11 iterations, you already get something that's not changing at all, or it's not changing that much. In most cases, yes. So you can see that the numbers start changing very, very little from one iteration to the next. So you can see just with this very simple example that this actually works. Right? It's not just a matter of theory, that you can actually make it implemented, and it's actually very simple to run. Like I was mentioning to someone during the coffee break, if you guys want, I can make the code available to someone, and then make the slides available. But basically, this is where all the magic is happening. I mean, there's a little bit more code that's basically reading the matrix and doing a little bit of magic in the background, but this is what you need to know. So this is how you get the Google matrix. That M is basically the alpha in the equation, is what is the probability that you will jump randomly. So it's just calculate defining thing and giving you the Google matrix at the end. And then the power method is literally, it's all being done here. Just multiplying the matrix by the current value of x0, so you get a new x0. And then I'm storing the previous value so that I can compare them and see if it's smaller than my tolerance, and then if it is, I break it. So with this little piece of code, you could build Google if you wanted. Of course, there will be some other problems in the process. So, moving on. Now, this is what happens if you actually run something like this in an actual web graph. So this is this was run on, actually I should have a reference for this, but it's not mine. This was run on two versions of, or rather two large crawls of the entire web, a large fraction of the entire web. They were measured in 2001 and 2003. You can see that, of course, they change a little bit from one year to the next, which you kind of expect. But the reason why I'm showing you this plot is basically this line over here. And this line is basically telling you that it's going as you would expect from the analytical result, and it's mostly corresponding to the integrity. It's not exactly the integrity, but it's very close to the integrity, because that's what the function of the integrity is very, very close. So it's not linear here, although it tends to be linear in this region. For intermediate, let's say, degrees, so not for very small degrees, not for very large degrees, but it tends to, in the middle, it tends to be more or less linear. And of course, it doesn't work for very small degrees and for very large degrees, because very small degrees tend to be very peripheric, so they are hiding out in the back. And then for very large degrees, you have very small numbers of nodes, and they're all very connected to each other, so it kind of works a little. So our assumptions start fading a little bit. So, what else? Yes, so now let's talk about something that's even more fun. An actual network, like that you've probably known that they've used to get here. Right? So this is the airport network, which you can't really see, but basically there's a bunch of little lines over there. Each node in this network corresponds to an airport. Lines connect airports based on airline connections, right? So if you are in New York, you can go to many places. If you are somewhere over here, you can't go to that many places because it's a small airport and it's not connected to anyone. So this is the degree distribution, the weight distribution. So this is the distribution of the weights on these edges. So how many people can fly regularly between 92 airports. And of course, you see that these are very broad-tailed. And some people will claim that these are power laws. It's not necessarily clear, but it was very fashionable to claim things are power law at some point. This is, so OKK, so this basically says that you actually have, that the weight on these edges are actually correlated strongly with the degrees of the nodes that they're connecting to. And if you think about it, that's kind of cool. And in this case, it's very intuitive why it should be like this. Right? If you're connecting two very large airports with many connections, then you have many people traveling between those two airports. If you're connecting airports, very small airports, very peripheral airports, then you won't have that many people going between. Right? So you expect to have, for instance, the largest airport by number of connections, I think, is Frankfurt. So between Frankfurt and Paris, for example, you have many people traveling because from each of them you can go to many other places, while between more peripheral airports you have very few of us. The traffic per node, so this is the top, so you can think of this as being the strength of the node, so when you sum over all the weights of all the edges connected to a specific node, and this goes as the power of the degree. So again, because the more connections you have, the more weight you have, the more people are trying to go there. One thing that's interesting to notice here is that these things are not linear, so that this has an exponent that's not 1. And so what this means is that there is an intrinsic value that you can observe on the network given to the fact that you have more degree. Right? So what this means is that if I multiply my number of connections by 2, I don't just increase my traffic by 2, I increase it by a factor larger than 2. So I'm getting, the fact that I'm connecting to more places is making it more attractive for people who connect more, and it's more attractive in a way that's more than what you would expect simply by the fact that you're doubling the connections. And this is the diffusion coefficient, basically between nodes of degree k and k prime, which again goes as a power law in this funny definition. And now you can complete this game, right? Now I can write the master equation and say very well, what is the change in time of the number of walkers, or the number of passengers, if you want, in nodes of degree k as a function of time, and you get so you have the same equation you had before. But now you can start plugging in things, right, into an actual real. Oh, here we go. So now you're plugging in all the expressions, and now you start seeing that text starts popping up. Yes. So this here, of course, is just the total traffic in those of the case, so the total number of walkers, if you want. You get this factor of k to 1 plus theta over there, and you get something that looks very similar to what we had before for the case of uncorrelated networks, but now you have this exponent over there that's different. So in fact, you have this theta, 1 plus theta, the same thing there. So when you do this, basically what you get is this. So you have the variation on the number of walkers by time is basically the total traffic that you have in that node. Because you've assumed that at each time step, everybody that's there leaves. Nobody stays in the airport. Nobody wants to live in the airport. Plus the number of people that you get from the other ones, right? But now instead of being this simple factor that you had before, now it depends on this data that basically is giving you a measure of the weight correlations for the edges. And you can find that the total traffic for each node is basically a constant. So it doesn't depend on time explicitly. And this transition is going to seem a little weird until probably tomorrow, but this will make sense in some way. So here we're talking about airport networks, and now I want to kind of maybe switch topics a little bit and start talking about epidemic models. Now, of course, as with everything that comes to complex systems, you have different ways of looking at it. So you can look at different approximations. I saw this in the beginning when I showed you, okay, you have this little process happening on this network. You can look. Excuse me. You can look at it on the macroscopic level or the microscopic level. Here, the case is a little bit more complicated. Here, you can look at many different ways of approximating the system, right? So you can start with a homogeneous mixing. which we're going to talk a lot about today. Right? So this corresponds exactly to the homogeneous mixing, the mean field approximation we already saw earlier today. Then you can start adding social structure. This is more or less the equivalent of looking at degree blocks, right, and starting putting a little bit of correlations into the system. You can move entirely to contact network models, where you actually have explicit connections between individual nodes, individual people, and then you see the process happening around there. Multi-scale models, where you try to combine multiple scales of approximation at the same time. So in some instances, you will consider people as if they were completely indistinguishable from each other, while in other cases you consider them as being individuals. And of course, then you have agent-based models, where you're literally simulating the lives of all the people in a single city or a single country, or even a single continent. I think the largest one right now is for all of Europe. And there you literally have, so for the case of Europe, if you have, let's say, 400 million people, you have 400 million agents in your city. But in the end, I mean, regardless of what level approximation you're having, what you end up with is always something that looks something like this. Right? You have the beginning of time when not much is happening. You have a very quick spread at some point. And then if you assume that people are recovering from the disease, you start seeing this decay over there. If people don't recover, you basically saturate and that you get the same curve we were seeing before, right? But for the little nodes changing colors. Since you could never stop being at state B, you just stay up there forever instead of seeing this. But you'll see that that's not always the case. So let's start with very simple cases. And here, right now, everything is completely homogeneous. Everybody is exactly the same. And I'm going to do everything analytically in a very simple way. So this SI model, so in epidemics lingo, S just means susceptible, I means infected, or infectious to be precise. And what this funny little thing means is, if you are healthy, you talk to someone who is sick, with some probability beta, you become sick. Right? It's the simplest possible case, and it's exactly the same thing I was doing for the little nodes changing colors. Right? You are A, you talk to someone who is B, and then with some probability you become B. Now you can write these equations directly, and this you recognize as being basically the macroscopic master equations for these two states. Now you have to distinguish between the two. So you have one for susceptibles, one for infected, and you'll see that these are all symmetric also, right? And this kind of makes sense. If you are here, you go there, so any loss here corresponds to a gain there, basically. Right? So you have people going from S to I only. Right? So that's in this sense of this arrow. And that's why I like these little graphical representations, because they make it very clear what is happening. So, and my pretty little animation of what's happening is if you start with someone that's infected there, it will start infecting people around himself, and then it will basically affect everyone after a while. If you run a little simulation, which I don't think I actually have an actual demo for this, but basically what you get is something like this. You start with everybody healthy and one guy sick, and afterwards you get everybody sick and nobody healthy. Right? So this is the complement of what we were seeing before with the node colors. Right? Before I was only plotting the blue line, but you can also plot the green line, which is the number of A's in the system. The number of A's, of course, goes to 0 because everybody becomes B. So, moving on, you can, of course, simplify this a little bit because you know that S and I have to be constant. Right? You can only be in these two states. So the number of people in one state plus the number of people in the other state is the total number of people. It's not surprising. So you can get rid, basically, of one expression and focus just on the other. So here you can just say, okay, the change in the number of infected people is beta times the number of healthy people, which is just the total number minus the number that are already there, times the probability that these people are interacting with someone that is sick. Right? And since this is the homogeneous mean field approximation, you are equally likely to interact with anyone in the world, and the probability of interacting with someone that is sick is just the number of sick people. For some reason that became very small. So, but you can linearize this and say, okay, in the beginning of time, this value of I is actually very small, so I can kind of assume that this is more or less n, and that n will cancel down. So you simplify it into this behavior, and you get basically this exponential growth, right? And this corresponds, when I showed you that little diagram, to that part when it was going from 0 to almost 1, it was just going straight up. And so that's this exponential growth. And this is something that you see pretty much in every epidemic process or any process of this type. You start with very few, and then it grows very quickly, and then something else must happen because of the finite size of the system. Now, if you put this same on a network, now we have to consider that there are different types of nodes, right? So we're going to do this now in the degree block approximation. So now the equation looks kind of the same, but now you have an index of k over there. And what this is saying is, so this is the change in the number of infected people with degree k, the times t, is the probability of infection for contact, the number of healthy people, which is 1. Oh, and here I'm using densities, right? So I'm not counting, I should have made that clearer. I'm not counting exactly how many people, just a fraction of people. So I'm dividing everything by n. And that's why you have the little letters instead of the capital letters. And that's why here you have 1 instead of n. Because it will be n minus big I k divided by n, but I'm just making that 1 minus little I k. K, which is the number of connections, right? So if you think about it, this is simple. This is how many people you talk to, and what is the probability that you're talking to someone that is sick, times the probability of you becoming sick when you talk to someone that is sick. And that's what that beta is. And now you need, instead of just having the I over n thing that you had there, now you have this mix, something that's called a mixing term, right? And this is telling you how each node of class of degree k is connected to all the other nodes of all the other degree classes. And this is given by this funny thing for an uncorrelated network. Right, so this is the equivalent of what we saw a few minutes ago of this P of k prime given k, right? So the probability that you're connected to somebody. But now it's a little bit more complicated because you have to sum over all the k's, but you get, in the case of uncorrelated network, you get something like this, which again does not depend explicitly on the value of k. So you can remove the k index over there because it's a constant for every degree class. You're summing over k prime, and that's the only variable that you have there. And yes, so now you can of course play the same game. You can linearize this thing, and you get this expression, and you get this one. But now you also need to figure out how the hell you're going to calculate this thing, right? Because this is weird. You have this theta function that's hiding over there, but this theta function actually depends on the sum over all the values of I, which is hiding over there. So you got to figure out how to do this. And the way you do that is basically you start with this equation, you multiply it by this fact over here, you sum over all that, and you get the master equation for this theta. Does that make sense? Do people want to shoot me now? Not yet. Good. Right? So if you're going to go from here to here, you have this expression that relates this I of k to this theta of t. Right? And to go from here to here, what do you have to do? You have to multiply this expression by this. I should have put a little drawing on this. So you multiply it by this factor here, which is constant for a given k prime. Right? You multiply it over there, multiply it over there. Then you sum over all the k's, and you get this after some relatively simple calculation, which is basically the beta times the second moment of the degree distribution, so the average k squared, divided by the first moment of the degree distribution, just the average k, minus 1 times this theta. Right? And basically what this expression is giving you is a way out of this loop, right? Because you're trying to calculate I of k, or I, but by doing this you had to define a new quantity, which was theta, which give you another expression, right? And in some cases it even happens that you can't close this, right? You define this theta, and then you need to define something else that then give you something else, and you have to keep going down and down and down, and you follow the rabbit hole because you can never close this system of equations, right? But here you can close it very, very easily, because now you have an expression that is self-contained, right? You can solve it. And this gives you the value of theta of t that you can then plug in there and get the value that you actually want. Still nobody wants to join, that's good. And then the solution you get is something like this, right? Which looks a bit scary, but it basically has the same form as before, right? You have an exponential factor over there, and then you have some constants multiplying, and this basically gives you what is the time scale, right? So how fast it's growing this exponential regime, and this will depends explicitly just on the properties of the network, right? And in particular depends explicitly on the first moment and the second moment, which you'll see popping up many times in the rest of this hour or so. So, moving on, yes. So I'm just rewriting that a little bit in a funny way. So this is when you sum over all the IKs, so this is the total number of infected people. So this is the total prevalence, the total number of sick individuals in your society. So you're just multiplying by P of k and then summing over all the k's, and you get like this, and that's how that k becomes average k over there. And now this expression, which is the one we saw before, basically tells you, because this is exactly an exponential expression. Yeah? So this is just the variation of something being linearly proportional to that same thing, so you get an exponential growth with no threshold. Yeah? This is an important point. Yeah. No threshold. Right? And what this means, this no threshold, what does that mean? Right? So here threshold in epidemics terms, threshold means what is the number of people or what is the minimum value for some parameter that gives you a large fraction of the population infected, right? Because it's easy to see that if the disease you're considering does not spread very well, then it's very hard for people to get sick, so the disease will die. Right? There will be no epidemic. You have 1 or 2 people that get sick, and then it doesn't spread any further. While if the disease is very contagious, then it will spread very quickly and will infect everyone, and then we all become zombies. So zombie. You can think of the zombie apocalypse as being a very contagious disease. So no threshold, because this is a very simple model, and like I showed you before, I mean, I've been basically talking about the same model in different ways for the last 3 hours or 3 days, depending on how bored you are. And it's all the same thing. You start with just one guy, and you can infect everyone because everybody will get infected eventually. Now let's look at something a little bit more complicated, where not everybody will get infected. Right? Now you have to add another class to the system. Now you say, I have healthy people talk to sick people, because apparently they like to do that. And with some probability beta, they get sick, but then they recover and they feel better, and then they go to the R class, the recovered class. Right? And these are people that used to be sick, but are no longer sick, but they can no longer become infected either. Right? You are immune to the disease now, which is pretty cool. So now my little simulation looks a little bit different. Start with sick people, he infects a few more, but then he recovers, and then you can kind of see that now you have this combination of things. Right? And you can even see that it's possible that the disease will die out before it infects everyone. Right? Not everyone will get sick, which is already a good thing. Not everybody will become a zombie, which is because zombies can get better. Now you have 3 classes, so you have 3 equations. So you have susceptible equation, the infected equation, and the recovered equation. Again, if you sum, I mean, this was very clear in the previous case because the equations were exactly symmetric. But if you sum these 3 equations, they have to add up to 0. The reason they have to add up to 0 is because I'm keeping the population constant. Right? The number of people in society does not change. Right? They can become sick, they can become recover, they can become whatever they want, but the total number is 0. The total number is the same. So when you sum all the variations, it has to be 0. And if it's not 0, you're doing something stupid. Now the plot becomes a little bit trickier, Now you have again the green guys that are healthy going down to some value. The blue guys, which are the infected guys, go up and then go down. So you start at, right? So this is exactly like that schema I showed you in the beginning. Start with 0, then you have the exponential growth, and then it starts going down. And this red curve is just the number of recovered, right? So this is the total number of people who were sick at some point. So in a very, very simple way, and this is basically what this equation here is telling you, R is just the integral over I. So it's the sum over all the people that were sick at some point. Questions? Yes?
The one was always just blue because never talked with people who were ill, or, I mean, it was independent from the beginning, or it was not just...
I'm not sure I understand. So what's the question? Sorry.
I mean, because you said that some people can be blue always, yeah?
Some people can be blue always.
I mean, they can...
Ah, yes. So, yes. Oh, you mean here?
Yeah,
Okay.
so...
Yeah, these colors don't match
This
those
is
colors.
just because disease was killed,
Before it reached them. Yes. So those people were always healthy.
but it's not just because they were so strong to not get this. I mean,
No, it's pure luck.
about the independence is just
They're just lucky. I mean, here there are no strong people and no weak people. Everybody has exactly the same probability of getting infected. Any other questions? So everybody will become a zombie if they get attacked by a zombie. But that will feel better, so it's okay. So you have these equations. Now you can linearize again. And here you're linearizing basically means you're assuming the process is in the beginning. So t is very close to 0. This means that R is also very close to 0 because you haven't had time to accumulate sick people yet. And that you can do the same approximation as before, so you get something that looks like this. Right? So here it's saying that the change in the number of infected people at time is basically the probability of someone becoming sick minus the probability of that person recovering. Right? So you get this exponential growth. But now you'll see that the exponential growth is a little bit more complex. Right? Because now you have the interplay between two factors, between the number of people that are getting sick and the number of people who are recovering. And so you have beta minus mu. And every time you have an exponential factor like this, one thing minus the other, you define, for some reason this should have popped up later, but anyway, you can define this value, we call this R naught. And it sounds cool. And it's just beta over mu, right? So what that means is you pull the mu over there, and then you get beta over mu minus 1. And what that means is this will grow exponentially if this quantity is larger than 1. Right? Because if it's smaller than 1, then when you subtract 1, it becomes negative and it dies. So this is basically giving you the threshold for the disease. Right? If these parameters are such that this thing is smaller than 1, then you have no epidemic. You end up with just a few zombies, but not many. What if it's larger than 1? Everybody becomes a zombie. So continuing in our equation, so again if you want to take it a little bit further, you have to define again the mixing term, which like I said is a conditional probability. Again, for non-correlated networks, you get the same expression. And you get again an exponential increase in this mythical omega function. And so basically this allows you to define this epidemic threshold, these R naught, based on the structure of the network, right? So again, you're getting the second moment of the degree distribution and the first moment of the degree distribution, and basically the ratio between the two. Now, one very interesting thing about that's hiding in this expression is that if you have a network that is broad-tailed enough, so it's basically if it's a power law, what will happen is that this value over here, k squared, the average, the second moment of the degree distribution, will be much larger than the first moment of the degree distribution, right? Because you have these very big guys with very large degrees, and these skew the average a lot. And what this means is that in the infinite limit with a very large network, with a sufficiently skewed degree distribution, this epidemic threshold will effectively be 0. Right? And so, and this for me is the perfect illustration of how the same process, which is a very simple process, and you know that it has to go up and it has to go down, blah, 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 and that it has to obey such that this threshold has to be larger than a certain value, etc. Yes. But depending on where you're running the process, so what is the structure and the the substrate that is underlying the process, you can change the behavior a lot. Right? So what this means is that it has to be such that if the network is skewed enough and as a Broad-Tailed degree has a scale-free degree distribution, you have no epidemic threshold. So this was shown a few years ago, maybe 2001, I think. And basically what this showed is that if you have a network structure like you have in social networks, tend to be very broad-tailed, very, very skewed, you will always have an epidemic. So you will always have a finite fraction of the population becoming infected before the disease dies off. Which if you think about it, is something very scary in some ways. So now we can do something even crazier, and now we say, yes, but this is even scarier, and now even the people who recover from the disease can become sick again, right? They can get reinfected. So now instead of having an R compartment there, you have an S compartment. So you start being healthy, you become sick, you talk to someone who's sick, you become sick, and then you recover and you become healthy again, and then you can repeat the process. Now you go back to having only two compartments, only susceptible and infectious, so healthy and sick. Now the populations over time look something like this. You start with everybody healthy and only one person sick, and at some point you find this equilibrium point where the total number of sick and the total number of infected people becomes constant. Right? And this will become constant basically when the probability to go from here to here becomes the same as the probability from going from here to here. Right? So this is a very good illustration of a dynamical equilibrium. Right? The number of people becoming sick is equal to the number of people that are recovering, and so it stabilizes. And so it's like a detailed balance condition. And that's why you get something like this. So now the simulation looks something like this. So you can have a fluctuation, you can increase, but then you can recover, but it can continue going on like that forever, with people getting reinfected again and again. So going back to our original equation, now it's easier because you don't have because this recovery term basically is putting back things into the susceptible compartment. Now you have to define two quantities. You define this theta, you define theta k, and of course the total omega k and omega. So this definition is the same, and this is just the sum over all degree classes of balance, is the total value. Now you can play the same game and define again what is the temporal evolution of this quantity, and you find something similar as before, which again will give you an exponential factor, and you can see that this is a linear term on the quantity itself. And so you get this form for the epidemic threshold, which again depends explicitly on the first and the second moment. Now you can try and find the stationary state. So the stationary state is when the number of infected individuals becomes constant, so it no longer depends on 0. So you can play the same game and just set it equal to 0. When you solve it, and you get something like this. It depends, of course, on the value of theta k. So this is an infinity. You can also try and solve it, and you get this weird little expression. And here I'm putting infinity to represent the t going to infinity. So, and now the Abelian threshold is set by basically the existence of a non-zero solution for this function here. So, and this is how you do it. Basically, you do it graphically by plotting the two things and see if these two lines, so this is the diagonal line, and this is the actual function, intersect in a point that is not zero over there, then you find a solution. That's how you numerically calculate this value, but it exists. So, and you can define that as being basically that this quantity here has to be larger than 1. And that tells you that this has to be larger than 1. Oops. Which basically tells you what is the academic threshold of the system. So even if you, which again has the same problem we saw before, for largely scale-free networks, this value, this thing has, basically beta over mu has to be larger than average k over average k squared, and since k squared goes very quickly to infinity, this basically has to be larger than 0, which basically means that you always get an epidemic, and you always get a finite fraction of the population infected at infinity. And you say, okay, this is great, but we're talking about these very simple things, right? We're talking about these networks and assuming that everybody with the same degree class kind of behaves the same way. Does that actually mean anything? What about something more realistic? That brings us the idea of dynamical networks. So this is a very simple model. So here what I'm doing is each node has some probability of being active at any point in time. Right? So at each time step, you give a finite probability for that node, that specific node to be infected, to become active, right? To create a new connection. So at each time step, whatever nodes that are active create a connection. Right? So basically, you wake up this morning, you decide you are active, and you come here and you get a connection with me. Right? And then you go home, and that connection disappears. So at each time step, you have a different set of connections. And of course, some nodes can be connected in one time step and not in another, and this can change from time step to time step. And if you have a lot of patience, you can make pretty pictures like this, where you have stuff rotating and connecting. It's awesome. But the idea here I'm trying to show you is that this is very dynamical, right? At each time step, you have a different network somehow that's based just on the connections that exist in that time step. And the next time step, the connections can be completely different. Right? And some nodes will be active, some nodes will not be active, some edges will be there, some edges will not be there.
Excuse me?
Yes?
What is the difference between temporal network and dynamic network?
I like to call it dynamical, people like to call it temporal. No, it's a temporal network. This is it's a matter of terminology. There's also many ways of defining temporal networks and different models of temporal networks. So, but basically what you have is, as a function of time, at each time step, even though the nodes are the same, the connections between the nodes are not the same, because not all nodes will be active at every time step, and not every edge will be present at every time step. And usually what people do is they ignore all of these things. They stack all of these networks together, and they just an integrated network, right? So just summing over all the things, and now you have all the edges that have ever been present in this network are there now. And this is something people have done for very long, because somehow the technology, the techniques to deal with temporal networks didn't really exist until a few years ago, when people started actually looking at this thing seriously. Now, we define this basically in a way that at each time step the network looks different. So not all nodes and edges are present. Static network aggregation over all the time steps, so you just put the union of all the graphs, if you want, or the union of all the GCSE matrices, if you want. And for each node, you give it an activity rate AI, so it's a probability that that node I is active at any given point in time. So at every time step, each node flips a coin and decides if it's active or not. Oops. Yes. And you define some average number of connections per node. It's not too important. And the activity potential, which is basically what is the actual, which is the actual probability. This is a rate. This is an actual probability. And this you need basically this eta there for the case when the system is changing in size and you can actually have a lot more activity in one point in time than another. So, and this is a way of normalizing that out. And now I've got, so and basically what this is saying is that with a given probability, AI times delta t, node I will create M links. And so this is exactly the same idea, the same process as we hate me, you don't want to kill me. When you're talking about preferential attachment, at each time step, one node creates one link. Here you have at each time step, each node that is active will create M links. So, and now let's look at our favorite zombie process and how people become infected. Questions? No. Okay. Just insults? No.
So this activity
Yes.
of the node AI, so it means the nodes are always not present in the graph.
Yes.
In the temporal network, I was thinking the link between the nodes keep on changing with the time.
Yes.
But the nodes are always present.
Yes. So you can think of, so the simplest example is you think about a phone call network, right? Today you call your mother, tomorrow you don't. Right? You and your mother still exist, but the connection isn't there. Is there or is not there, depending on the day.
But with the activity node, the AI, if I give you the, I should not say like that, but my mother exists today or it may not exist tomorrow, but then again,
Yes.
tomorrow it may exist. But is that
So I'm telling you that each day there's a 50% probability that you will call your mother. Right? So one day you will, the other day you won't. Sometimes you call them 3 days in a row, sometimes you won't. So, but now you can basically try to redo this process that we just saw and try to put this detail in. Like now instead of people always connecting in exactly the same way, you are active or not, and you can create connections or not, and this changes how you can become infected. Right? And what I'm trying to do here is trying to say, okay, now that we have, even in this very simple process, as soon as you put in a little bit more complexity, as soon as you add this temporal component, this dynamical component, you change the process a lot. Right? And actually, this is why I like to call it dynamical and not temporal, because the other models have a t there too, so there's also time hiding in there, but it's a fake time, it's not a real time. Right? Even in the Barabasi-Albert model, there is a time hiding in there, it's the process time. So now you play the same game, you have to define the same type of master equations, but now instead of considering degree classes, because you don't have degrees, you just have nodes, you actually consider activity classes. Right? So instead of being I sub k, you call it I sub a, which seems very simple, but it's not really like that. And here what you're saying is, okay, the change in the number of infected people at times t equals minus the number of people that recovered, because that's the easiest term, right? Plus the number of active, healthy people that you interact with and get infected, right? And this basically corresponds to you being home sick and somebody, a good neighbor that's healthy comes and knocks on your door and brings you soup and you make them sick because they're not a very nice person. Plus the case of you being sick and still not being a very nice person and going around knocking on people's doors and trying to get them sick. Right? So because you are infected and active, so you go and you create connections to people and you transmit the disease along these connections. Well, here it's a healthy person that is active and creates a connection to someone that is sick. So you have to consider these two processes. So it looks like a very scary equation because now you have integrals because the activities are continuous instead of being discrete. So wherever you had sums before, now you have integrals. That makes it very scary, but it's basically the same thing. You put things in the box, and you take things out of the box, and you ask how many things are in the box. If it was complicated, I wouldn't be doing it. So now you have to define these two quantities. You say, okay, now we have the change in I as a function of time. This is the total I, and this is again our omega function, is the integral over all the activities of the chain of this expression, basically. Which you can write in this simplified way, which is again the change in the total number of infected people, plus this infection rate, infection probability, over the number of infected people, plus this term omega that you can define again using this expression here, which looks a little bit scarier than before. But you will notice that it has the same type of structure. Right? You see again that the first moment of the activity distribution and the second moment of the activity distribution are there, while before what you had was the first moment of the activity distribution and the second moment of the activity distribution. So far, it looks very, very much like we just replaced k's by a's and sums by integrals, and everything should be the same. We will see in a second that that's not exactly the case. Spoiler alert. So moving on. Now, if you have two things and you want to make sure that these things grow, you have to define the mathematical trick you use is you define this Jacobian, which is basically all the cross derivatives, and you want this thing, the determinant of this thing, to be larger than 1, or to be positive. The values I get back to have to be positive. Let's be precise. And when you do that, when you set this, you calculate the eigenvalues of this thing, you set them equal to 1, you get this threshold. Right? And what you notice now is that this thing looks very much like what you had before for degrees, which actually I'm not showing it here. But now the expression is a little bit different, right? So now you have the first moment and you have the second moment, but the second moment shows up with the square root, so it's a little bit, so the functional dependence is actually different. And so this means that you're not just renaming things and relabeling things. This temporal aspect, or this dynamical aspect, is actually making a difference in how the things spread. Right? Now, how does this compare with the process that we saw before, where we actually had just a normal process spreading with just the degree classes and the different threshold? Right? So this has to make a change. So here is the comparison. So here, this is I infinity is basically the number of infected people you have at infinity when t goes to infinity. So what is in that plot I showed you in the beginning, so where does that flat line lie? As a function of R naught, so the function of that parameter I just showed you. Which you can't really read very well, sadly. So the circles, the black circles, are basically the calculation I just did. So all the activity, all the temporal details hiding in there, putting in there. And the squares and the diamonds are basically the typical process I showed you before, where you just consider the network to be fixed, and you let the process running on the network. And you're using the network that you would get from this same process, from this same activity process, but now you're just integrating the network over 20 time steps or 40 time steps. And this little red triangle over there is basically the threshold that you predicted with the Jacobian calculation you just did. So you can see immediately that if you run the process and you run the simulation in the full activity process, you get the threshold exactly as you would expect. But you also notice that the threshold that you get is actually much larger than what you get in the static network. Does that make sense? So basically what this is telling us is the fact that if you consider the network to be static, you're basically saying at every time step all the edges are there. Right? If the network is dynamic, if the edges can come and go, this has to slow down the process. Right? If the edges are never there, the disease cannot spread. If a specific edge only appears at the last time step, there is no way the disease can spread between those two nodes before that. So this has to slow down the process, and basically this is what this is telling you. It's saying that the fact that real networks, and in particular real social networks, where epidemics are actually happening, are are actually slowing down the process, and it's making the zombie apocalypse much less likely because you're actually slowing down this thing. This temporal component is having a strong impact on the spreading of the disease. So it's not the fact that as soon as you have a disease in a network, it will explode and infect everyone. You have to take into account the temporal components. Yes?
Would it be possible to make the static network more precise? To calculate not the degree, but taking the activity into account, for example, of strings, instead of the degree for the classes?
No, I don't think that would work. No, because basically the big problem is that in the static network, you have edges that are always there, right? So the disease can always spread.
Yes, but if you have a node which has a very large degree, but it's not that active, and this particular rate network, these edges, although they're a great number, will have a very low value.
Okay. So what you're saying is you want to modify the activities so that you get the same thing.
Okay.
Sure. And you could probably do that. I don't know exactly know how. It can probably be done. Might be an interesting Java project. I never really thought about it. There's probably a way to do it. I mean, some people know a lot more than this than I do. So Gleam. Now we're going to talk about real epidemics. Yes?
Yeah, I'd like to ask you, will you comment on how to estimate your team in general?
Oh, yes, I should. Sorry, I thought I mentioned that. The easiest way, so the way this is done is very simple. For each time step, you count how many active edges there are, and the activity for each node is basically the fraction of the total number of edges that's in the system. So it's very simple. I should have a slide showing this, and showing this for real networks, but I don't know what happened to it. I was thinking with the slides even this morning, so maybe something like that. And that's why I was slightly late.
May I have yet another question? So actually we have two different dynamic processes here. One
Yes,
is the
exactly,
one
yes.
is the network itself, the dynamics of the network, and
Yes.
dynamics of the diffusion
Process on the network, yes.
So the question is then, what is the step here? If we treat the step as the step of the evolution of the network itself, what can happen within the single step of the network evolution in terms of the diffusion process?
Yes.
So
Exactly.
it is one to one, or maybe, you know.
I didn't really want to go in that direction, but we can do this. But basically what we have here, if you think about it, is two different processes. Right? You have the epidemic process and you have the network evolution process. Usually what people have done is they considered these two things as separate. Right? You have either the network is changing so quickly that you don't care too much about the changes, and it's okay to use the homogeneous mixing approach because everybody can connect to everyone and it doesn't matter because it's so quick. Or the network doesn't change at all, it's frozen and it's static, and you just have the epidemic moving on top of the existing edges. In this case, what we actually have, and that's why things are interesting, is that the two timescales, the timescale of the network and the timescale of the process, are actually similar. So things can change, both things can change at the same time time step. And that's what makes this interesting, is you find it's this intermediate regime between the two classical ways of looking at this. You're looking at how the fact that you have two temporal processes with this very similar timescales, how they mutually influence each other. Sorry. But now I have like 10 minutes left, I guess. So 15. I didn't want to finish the morning of boring you too much without showing you some very pretty pictures. So I'm going to talk about GLEAM. So GLEAM is a very funny name. It's the Global Epidemic and Mobility Modeler Platform. And what this means is that this is an actual state-of-the-art epidemic model that actually tries to simulate the entire world and how a pandemic would spread on a global scale from city to city, from person to person. Right? And hopefully, after listening to me and getting bored for 3 hours, you can now understand exactly what's happening here. Because you already have all the theoretical baggage, let's say, to actually understand what's going on. So the way Gleam works is very simple. There are 3 different layers. You have the population layer, and this is basically where people live. You have the and so you have here the population layer. These little dots that you see there. I mean, here I'm showing you just the US and Mexico because it looks pretty, but we have this for the entire world. So we have where the people live, and these little red dots are basically the airports, where the airports are, right? So we're defining, for each airport, we're defining a population for that airport, which is basically the people that live close to that airport. Right? So each airports will be our nodes, and the population inside each node will be the population that is closer to that airport than to any other airport. Then you can connect airports, so connect cities, this very phenomenological definition of city, with airline connections. And you can pay a lot of money and get the entire database of all the connections every day at every time between all the airports in the world. And that basically gives you all these edges. And here, of course, the color of the edge goes from blue to red to show where the strongest are. And of course, the strongest connections are the longest ones, and the weakest connections are the shortest ones. And this is why I needed to show you first the airline transportation network before, so it will make sense now. So I'm not completely insane yet. And so this gives you basically a very macroscopic view of where people live and how they move by airline connections, so long distance connections. Of course, you usually don't fly between your home and your office. You might drive, you might take a train. In some cases, you might take a boat, depending on where you are. So we also have to define this commuting network that sits in the middle of these two. Right? So on one hand, you have people on the ground. On the other hand, you have planes in the air. And commuting somehow sits in the middle. It's connecting people, not at long scales, but not at too short scales either. So like between neighboring cities, because in the end, what we care about is between cities. So, and this you get, this information basically from census data. Okay? And then each city is now represented basically as one node with one population, and inside each city, what you have is an epidemic model. And this might look a little bit scary, but this is basically a small variation on an SIR model. Right? In the SIR model, you had susceptible people, you had infectious people, and you had recovered people. Here you have something called an SEIR model. So it's susceptible people, you have latent or exposed people. So these are people that have the virus in themselves, but they're not infectious yet. Right? So it's the beginning of the process. Then you have infectious people, and then you have recovered people. Here it's a little bit more complicated because you have 3 different classes of infectious people. Because you have to distinguish a little bit their behaviors. You have to say, okay, I'm sick, but I'm so sick, I'm staying home and I'm not traveling. I'm not going to work, for example. And those are the, what do you call them? Symptomatic infectious, no travel. So you're symptomatic, you're sick, you're infectious, you can spread it to other people, but you're not traveling. So you're staying within your city. You have the symptomatic infectious people that travel. So you say, okay, I'm sick, but maybe I'm not that sick. I really need to go to this conference and infect everyone, so I need to go. So I get on the plane and I go in Europe. And then you have the asymptomatic infectious, and these are people that don't even know that they are sick. Right? You're carrying the virus, you can spread the virus, but you don't really know, so you behave the same way. These people, because it's a reasonable assumption is that these people are actually probably less infectious than other people because it's not sick, they're not as sick, so they're not producing as much viruses, etc. So you can kind of reduce the infectiousness a little bit. You can define you have to define a bunch of probabilities, of course. What is the probability of you traveling if you're sick, or the probability of you spreading the disease if you are sick and not traveling, or if you don't know. So that's what all these things are. How long you stay in the latent state, so how many days you spend incubating the virus somehow. Because even if you are symptomatic no travel, you can still travel in this compartment. Right? So moving on now. You can do this for the entire world. And of course, the world tends to change a little bit depending on where you are, so you also have to consider seasonal variations, right? This is particularly developed, I helped develop this model a little bit, mostly to study like influenza-type illnesses, so things like the flus, swine flu, anything that, basically anything that you can spread by sneezing on someone. It's the most general definition. And of course, influenza-like things tend to be affected a lot by seasonality, and seasonality tends to change depending on where you are. No? I mean, during the coffee break, I was talking to someone from New Zealand. They just came from New Zealand, so they literally just traveled from summer to winter, right? In one or 2 days. So, because it depends a lot on where you are in the world. In one place, it would be summer, in the other place, it would be winter, and vice versa. In the middle, you have the equator, and it's always summer. It's wonderful, I hear. I should move there. Find a nice place on the beach. Anyway. So you have to define also this, how the infectiousness depends on the season, or the time of the year, right? And you do this in a very simple way. We just say it's basically a sinus wave, that it's lowest in the summer, it's highest in the winter. You're more likely to get sick in the winter than you're to get sick in the summer. If you live in the tropical area, then it's always the same, because there's really no season. And you have to define, to calculate exactly these things. I don't need to really go too much into detail here, but basically this is just to show that you can actually define these parameters. You can measure these parameters using empirical data and calculate what is the seasonality scaling. Because in the sense that we actually did this for the 2009 pandemic, and using empirical data from health officials around the world for the different countries, we were actually able to measure all of these parameters and calculate and make predictions about how the disease is going to spread, how the pandemic is going to spread. And yeah, this is just explaining a little bit on how those predictions were done. So we made this maximum likelihood estimate where we're basically trying to adjust our parameters to find what are the most likely set of parameters that match better the empirical data, so to speak. And here the empirical data was basically the arrival time of the disease to a specific country. So the first case detected in country X, that was so for each country we had this. And then we run our simulation and then measure what were the arrival dates for all the countries, and then tweak our parameters until we could match those arrival dates. And we did this for a few, and the idea was we would do this for a few countries, so for the first countries, the first country got sick, and then we could use this to predict what was going to happen next. By playing this game, we found this R0, so this epidemic threshold value, to be 1.75. Later, people doing actual virological analysis and actually looking at the viruses and understanding actually said that it would be around 1.75. No, it would be around 1.9, I think. So very close to what we measured in this very crazy way by just doing simulations. And there was two studies setting the same value. And now I said, okay, so you have this crazy model where people are moving around and traveling and flying and commuting and infecting each other. And can you actually make predictions, right? Can you actually do something? So here is an example. So the colors are basically showing you the epidemic curve, so in a very simplified way. So going from yellow to red, from 0.8 to 1. So 1 is defined as the maximum value of prevalence, so where the peak is. So, and it's showing you basically how spread out the peak is. And these bars are basically what our simulations are predicting. Right? So you can actually see. So now what I'm actually saying is, given that you have the arrival dates in the different countries, I can adjust my model and tweak my norms until I match those arrival dates. And then using those arrival dates, I can predict how the disease is going to spread from there on. Right? So the arrival date here, I think, was somewhere around here, if I remember correctly. And then you could predict what's going to happen right somewhere around here. And then you could predict what's going to happen next. So and find out where the peak actually is. And of course, you can do this for North America, you can do this for pretty much everywhere in the world. And you find these very nice matchings with some notable exceptions of between what we predicted ahead of time, and this was something that we published in early September, I think. And so somewhere around here we were publishing these results, and then we predicting what's going to happen 2-3 months ahead. And just for comparison, that's when people usually get sick, but for this specific pandemic, for the H1N1 2009 pandemic, people were getting sick much earlier in a much different way. And so, but the model was actually able to take that into account. And yeah, I think it's at 1:15. That's the first one. Okay, so I'm 2 minutes late. I promise you. So, but based on this, you can predict all of these, you can measure all of these things, and run a simulation that will predict and give you good results what's going to happen next. So you can actually observe how the disease was spreading. Right? So the disease was starting in Mexico over there, sometimes in February, and you can see it moving. Here, each line corresponds basically to the flight where the first person to arrive in that country sick flown, so you can see it spreading throughout the world. And then you can see also somewhere, you can see the colors also changing, which you should see now here when you get back to the US. You can see the colors changing, but giving you the prevalence of the disease. Here we go. Yes, so these orange shades over here basically tell you where the largest number of infected individuals are. So you can see the different cities and the different countries and how it's moving from city to city. Right? Right there we see Moscow basically infecting all of Russia, not China and India over here. It's really good. So, and the way so we did something even better. Now we said we have this model, we have this technology, we can do it, and you can actually let people play with this. So you can actually download the software, install it on your laptop, define whatever epidemic model you want, and run it in our service, well, their service now, and observe the results, and you can play with different scenarios. And it looks something like this. So it shows you the map of the world. It shows you where the infections are. You can click on each city and see the epidemic pattern, how it's going over time. You can move back and forth and those sorts of fun things. You can use whatever epidemic model you want. You can define it by hand, by literally drawing it and defining all the variables. And it's really available to the public. So, and I think that's it. I don't have time to actually show you how this works, but I can show you offline later if you like. So if you have any more questions or insults, go for it. Thank you.
Are you exhausted?
Yes. They're exhausted from listening to me.
We'll give you a couple of hours of